let's switch gears and talk about the concept of dipole moments. Okay. Remember, we talked about how when you have two atoms, let's represent them as two balls out here, and one of them is more electronegative. Let's say this one is more electronegative. Okay, they're connected by a bond in between. Then this atom will end up with a slightly negative charge, and this atom will end up with a slightly positive charge. Remember that? So when that happens, so when there is a what we're saying is there's an electronegativity difference between the atoms in the molecule. Okay, let's call that delta En. Okay, then the bond ends up behaving kind of like a magnet with two poles. One is a negatively charged pole, the other is a positively charged pole. Okay, and so if I drew a dipole, then it would look like this. It'll be an arrow, okay, and there'll be a little cross at the end of the arrow, and the cross sits at the positive end. You see how the cross looks like a plus sign? And the tip of the arrow sits at the negative end. So that's your dipole. You will represent the dipole in that way, okay? So all you have to do is understand which atom is more electronegative and then draw the dipole accordingly. So let's say you have this kind of a bond, HCl. Can you take a second and draw the dipole for this bond? So chlorine is more electronegative, right, than hydrogen. So therefore, chlorine should have a delta minus and hydrogen should have a delta plus. Therefore, the dipole moment, the dipole should look like this. All right? Okay. Now, that is for a specific bond. What happens in molecules that have more than one bond? So take, for example, carbon dioxide. We already know the Lewis structure of carbon dioxide, right? There's clearly more than one bond. Now, when I say more than one bond, I'm not talking about four bonds because technically there are four bonds out here, but I'm talking about two bonding regions. Okay, so the double bond treated as just one bond. Okay, so that's a bonding region. So for each of these regions, so for this region, that's a delta minus, that's a delta plus. Therefore, the dipole moment out here is going to be so that's the dipole moment for that region. And then for the other region, because that's a delta minus, the dipole moment is going to be this. See if that makes sense. Does that make sense? Okay. Now, here's the thing. So this is an example where you will actually see that dipole moments, when they're opposite to each other, they will cancel each other out. Okay. So what happens is the net dipole moment is going to be 0. Therefore, carbon dioxide has a net dipole moment of 0. Now notice carefully, each bond in carbon dioxide is not does not have a 0 dipole. It's just the sum of all the dipole moments in that molecule adds up to 0 because the dipole moments cancel each other out. Okay. As a result of that, this molecule is called a non-polar molecule. By contrast, this molecule is a polar molecule. Let's take a look at some examples out here. We already did HCl. Let's go ahead and do NH3. Now remember, to be able to predict the dipole, you need to be able to draw the molecule out first. So I'm going to give you, we've kind of discussed a lot of this already. So I'm just going to give all of you a few minutes, go ahead and try these molecules and predict the dipole moment. And then describe, I'll come and talk about it in a few minutes. So we already did HCl and carbon dioxide, so you can skip those. Let's do water. I don't know. Which one did you start doing first, NH3 or water? Who did NH3? Okay, and who did water? Okay, so NH3 wins. What? Yeah, did you do water? Okay. All right, we'll do NH3 first, then we do water, okay? So NH3, this is what the structure looks like. Remember, it's important to predict the shape of the structure. That's what NH3 looks like, okay? And notice carefully, the nitrogen is more electronegative, so the dipole moment should look like this. This should look like this. And that should look like this, right? You see how they're all pointing in the same direction, okay? But are they canceling out each other? Are they exactly opposite each other? No, because they're at an angle, right? Therefore, the net dipole moment should really be something like this, right? Therefore, and all you have to do is predict if these molecules are polar or not. So therefore, this is a polar molecule, okay? Now, let's do H2O. H2O, this is the shape of H2O. Dipole moment looks like that, right? Similar to NH3, right? So therefore, the net dipole is going to be like this. So therefore, this is polar as well. Okay. Let's take a look at CHCl3. And this should answer your question, Logan, whether does the arrow ever point inwards? You see, in these ones, the more electronegative atom is sitting at the center. So the arrow points inwards. Okay. In this one, this molecule looks like this. I'm not going to worry about the lone pairs on the remaining, on the outside atoms. But notice carefully, in this case, it actually starts to look, this is what the dipole moment looks like. Polar or non-polar? Polar. In SF6, it's an octahedral molecule, so it's symmetrical, okay? So between sulfur and fluorine, fluorine is more electronegative. So these dipole moments kind of look like this. Sorry, it's becoming a little messy. But notice carefully, I'll use a different color. Notice carefully, do you see how this arrow and this arrow are exactly opposite to each other? Therefore, these two will cancel each other out. Notice how this arrow and this arrow are opposite to each other. They cancel each other out. Likewise, these two cancel each other out. Therefore, the net dipole is 0. Therefore, this molecule is non-polar. All right. Okay, I'm going to give you some hints out here. I'm just going to give you the answer out here, and you can figure out why it is the way it is. This is non-polar. Try to figure that out why. This one is also non-polar. And that's it. Actually, this one is slightly polar. Let me just double check, double draw that one. So you have C, you have H, you have Cl, you have H, you have Cl. That's going that way. That's going that way. And there's not much happening between the carbon and hydrogen because there's not much electronegativity difference between them. Okay. So therefore, your net dipole is actually going this way. So therefore, this is polar.